Hello, everyone, and welcome to the presentation about our work, Learning Multimodal Affinities for Textual Editing in Images. This is a work by Or Perel, Oron Anchel, Omri Ben Eliezer, Shai Mazor, and Adar Averbuchelor. Allow me to quickly introduce myself. My name is Or Perel, and I'm a research engineer at AWS Textual. For those who are unfamiliar with it, Textract is a cloud-based service for document analysis, which relies on deep learning solutions. Let us start by talking a little bit about the scope of our work and the motivation beyond it. In our work, we assume the domain of document images, that is, pixels that represent semantically meaningful text. And here I find the Wikipedia quote quite fitting. Now, extracting information from document images is challenging, but we want to take this one step further and expand the idea to group editing. The problem we solve in this work is how to select or cluster meaningful groups of words which would ideally users want to edit at the same time. Let's briefly review the process through a visual example. Here we have a brochure which contains information about birds with varying levels of details. What would an edit here possibly look like? We could, for example, choose to highlight the bird names, or change color for bird names in Haitian Creole, or maybe even remove some of the measurement figures included. Notice how each word group shares common attributes, whether by font, by size, or by semantic content. To start the process, we first detect where the words are and extract their transcriptions. Then we cluster them using our method. We'll cover the specifics of how exactly we do that in the upcoming slides. Finally, after the clusters are extracted, a user may edit groups of words at the same time. We could highlight the red cluster of bird names, or maybe remove the cluster of bird size measurements. The focus of our work is finding useful clusters of words in a way that benefits users for group editing. Let us now move on to the problem formulation. The challenge is that the domain of documents can get quite diverse. Dense documents of mostly plain text, such as letters, forms, and receipts, colorful infographics, brochures, menus, and schedules, and even syntaxed images of sparse words captured in the wild. All of these are considered legit document images, and since this is a big domain, we do not limit ourselves to a particular training set, not even an unlabeled one. The method we present today is entirely unsupervised. It does not assume anything about the structure of the document. Despite their variability, document images have something in common. They normally contain semantic text, depicted through visual fonts, which is laid out in a geometric, meaningful way. Text properties are strong indicators to the purpose of words within a document. They implicitly inform readers about the group of words in a document. For example, in the menu to the left, we don't have to read the entire menu to tell that bold words indicate food names, and the small, slightly indented text represents menu item descriptions. Occasionally, however, visual cues are not unique indicators for word groups. For example, here, prices of menu items appear in bold font, much like food names. A more extreme example is the receipt to the right, where the entire document uses the exact same font. In such cases, readers implicitly rely on geometric cues or semantic ones. Notice how in both examples, the prices are well aligned in the columns. The receipt to the right uses mostly capital letters to emphasize item names. As for numbers, they appear in a few different places on the receipt. Their suffix or prefix tells us whether they mean an amount, some unit, for example, kilograms or percentages, all possibly belong in different word groups. So on one hand, we can cluster words into meaningful groups if we consider which properties they have in common. And on the other hand, the domain of document images is large. So we don't want to limit our solutions to a specific handcrafted set of rules. Instead, we will try to learn these clusters per document based on visual, language, and geometric features. Before we go on to talk about our method, we highlight the difference of our setting from previous works. Previous works, like that by Young et al. 2017, segment a document image into syntactic labeled regions according to labels of predefined classes, such as figure, section heading, caption, and paragraph. Our method is unsupervised and is focused on semantic affinities between words in the image. The number of clusters we generate is therefore dynamic and varies from previous definitions. Let's see what the algorithm looks like. Our method does not require a training set, but it does rely on a few pre-trained independent blocks. Note that in our setting, we assume we don't have access to the metadata of the document, meaning we rely only on the document pixels as input. First, we leverage an off-the-shelf OCR engine. An OCR engine takes an input image and provides the estimated locations of word bounding boxes, as well as their transcriptions. OCR engines differ by quality. Some provide complete lines, and some are geared towards specific target domains, such as dense text documents or sparse syntax images. Our method is not coupled with the specifics of a particular solution, but rather we assume the most basic functionality that all engines support, extracting word boxes and their transcription. Second, we train a font classifier on our own synthesized images of text. We've compiled a set of fonts and let the classifier predict multiple visual attributes, such as the font type, style, like italic or bold, and whether all characters are lowercase, uppercase, or mixed. After training converges, we follow the common practice of cutting off the last classification layer and using the network as a feature extractor. In our solution, we use the ResNet 50 architecture, but our method is agnostic to a particular solution, as long as the representation obtained is rich enough to capture the font information. Last, we use common word and contextual language pre-trained embeddings, such as FLAIR, or alternatively, the well-known BERT. These models were trained on very large sets of unlabeled text and capture the semantic meaning of the words of the context in which they appear. We are now ready to dive into the details of the full framework. Our method receives an input image of some document. The basic element in our work is words. Our goal will be to learn an affinity space of the document words, which will form our clusters for group editing. Our first step, therefore, is to use OCR engine to extract word boxes and their transcription. Isolated words are not enough to effectively analyze language-based features. Therefore, we group nearby horizontal words into contextual lines. To do so, we build a sparse, undirected graph. In this graph, words are linked if they contain similar geometric attributes. Specifically, we use weighted edges, where the weight between a pair of words is calculated by a closed formula as a factor of the horizontal space between the words, their height, and the aspect ratio of the image. The connected components of this graph form our final contextual lines. Note that we deliberately avoid sophisticated line extraction methods and paragraph grouping. We seek a conservative approach which favors accuracy over recall, that is, to avoid grouping words with different contexts into the same contextual line at all costs. Each word is now associated with a contextual line. Next, we initialize our learned affinity space by extracting a multimodal feature representation for each word and contextual line in the image. First, we apply the style encoder, our pre-trained font feature extractor per word crop, to obtain a visual representation f of s. This representation captures information about the font type and style. For content representation f of c, we feed the OCR transcription into a pre-trained contextual language model encoder like FLAIR by Akbik et al. Or BERT by Devlin et al. The representation of each word is conditioned on the representations of other words in the contextual line sequence. Our framework is general and does not depend on a particular choice of representation, so long it captures the semantic meaning of each word within its enclosing phrase. The last part of the embedding is composed of geometric information of the word box obtained from the OCR engine. Here, we look at the position coordinates and bounding box dimensions of each word. Geometry embeddings are in particular useful for capturing alignment of rows or columns within documents. The final representation per document word Z is a concatenation of the visual, content, and geometric representations. Typically, this representation is very high dimensional. Our implementation, for example, uses dimensions 512 for visual embeddings and 4096 for language. High dimensional representations are notoriously hard to cluster. Naturally, we would like to project the high dimensional representations to a lower dimensional space. Unfortunately, many times, non-learned methods provide a low dimensional space where the word clusters are still not clearly separable. For example, here, we show that the projection looks like using kernel PCA. The color scheme indicates the desired clusters. Notice that while the initialization is useful, the clusters are still not completely separable. Our goal then is to learn an encoder network f of theta, which will be used to project representation Z of word W to a low dimensional representation space R of D. We would like the new dimensionality, lowercase d, to be small enough to avoid the curse of dimensionality and allow for feasible clustering. We would also like it to be big enough to capture necessary information required for separating clusters on typical documents. We will couple our low dimensional space with an affinity measurement function, sigma. Sigma will convert the distance between words in the representation space to an affinity score, such that low dimensional representations, which are close to each other, get a high affinity score, signifying they should go into the same cluster. Pairs of words with distance representations gain a low affinity score and should go to separate clusters. Our architecture now becomes a Siamese network, f of theta, which together with the affinity score takes pair of word crops and outputs their predicted affinity. The Siamese architecture is lightweight and uses two blocks of dropout linear ReLU layers, followed by a final dropout linear block. Note that for a single word, the network f of theta outputs a low dimensional representation f of theta, Z in RD. When applied as a Siamese architecture on a pair of words coupled with an affinity function, the sigma is an affinity value between 0 and 1. To guide the optimization problem, we use self-supervised labels. The labels are formulated as weak constraints we generate between pairs of words. These weak constraints will be soft, in the sense that we allow them to possibly contradict each other. The constraints we generate can be roughly separated to three groups. The first and second groups are must-link constraints. Must-link constraints aim to pull together words that should potentially reside in the same cluster, meaning they have high affinity. Must-link constraints can also be intracontextual. That is, they are formed between pairs of words that share the same contextual line. Or they can be intercontextual, meaning they are formed between pairs of words from different contextual lines. To form an intercontextual must-link, a pair of words has to be similar in terms of visual, syntactic, semantic, and geometric criteria, with high certainty. Please see the paper for elaborated details on these criteria. The last group of weak constraints we generate are cannot-link constraints. Cannot-link constraints aim to push apart words that should reside in different clusters, meaning they have low affinity. Note that cannot-link constraints are always intercontextual. That is, they are formed only between pairs of words from different contextual lines. To form an intercontextual cannot-link, a pair of words has to be different in at least one of the following criteria: visual, syntactic, semantic, and geometric criteria. We use both types of constraints to generate weak labels of affinity score to train our optimization network. Must-link constraints amount to a label of 1. Cannot-link constraints amount to a label of 0. We now have a training set of word crops, their initialized features and self-supervised labels in the form of pairwise weak constraints of binary values. So we are now ready to train our Siamese network with binary cross-entropy loss. And this is what it looks like. We train f of theta through an iterative optimization, where at each iteration, we sample pairs of words and let the network predict their affinity. Note that we may also have pairs of words which don't have pairwise constraints at all. However, the system of constraints acts as a system of springs, ultimately pulling and pushing words around into clusters. During this optimization, words are first projected to a low-dimensional space by an encoder neural network. Then, words with similar attributes are pulled closer to each other, and words which clearly belong in separate clusters are pushed apart. Upon convergence, we obtain a learned affinity space over the word crops. Finally, we would like to leverage this learned space to group our contextual lines into clusters of highly similar elements. Given two contextual lines, we apply our trained Siamese network over each pair of words from these contextual lines. We then use mean likelihood estimate to decide if these two lines should belong in the same cluster. For the likelihood estimate, we leverage a voting mechanism, where each vote is the pairwise affinity between words in these lines. Finally, we construct edge-weighted graph of contextual lines as nodes, and their likelihood estimated affinity as edge weight. We prune edges with an estimated affinity below the threshold. The final clusters are obtained by calculating the connected components of this graph. Here are some examples of our algorithm results. Notably, the formed clusters correspond with the semantic division of words within each document. For quantitative evaluation, we also performed a user study. Please see the paper for additional details. Let's see, now we will talk about the interactive mode of our algorithm. After clusters are formed, we can finally perform group editing by editing a representative from the cluster and propagating the changes to the rest of the cluster. The number of clusters formed is dynamic and varies between documents. We therefore allow a refinement phase where users may enforce their own custom constraints as must links or cannot link constraints, according to their preferences. It's enough to define very few constraints and rerun a quick optimization phase to allow new clusters to reform. Behind the scenes, for refinement, we augment our training set with the given user constraints and continue to optimize the Siamese network. Our method enables a variety of novel applications spanning style, content, and geometric applications. We demonstrate two style-based applications. The first allows users to emphasize textual regions in the image. The other allows the user to alter the font type or color. The user can also select to propagate edit changes that modify semantic content within the image. For example, we can propagate mathematical expression for words that depict numbers or dates. We also demonstrate propagation of changes that modify the document structure. For instance, we can indent the selected text by a certain margin. We can also remove textual regions in the image and bring them back interactively as the user hovers their mouse over a nearby textual region. Finally, we will briefly discuss some limitations of our algorithm. The first step in our framework employs an OCR engine to extract the words from a given document image. Though our framework is agnostic to the specific solution used, our solution is still coupled with the performance of the OCR engine. As a pre-process step, our algorithm checks for overlapping words to increase robustness to false positives, but it is unable to recover false negative samples. That is, undetected words that the OCR engine misses. In addition, a core part of our algorithm relies on contextual lines. Therefore, the performance of contextual lines detection is crucial. Our implementation uses a per document statistical measure to group words into contextual lines, and may be sensitive to certain cases of outliers. So to summarize, today we presented a novel method for clustering text in document images guided by multimodal affinities. We also discussed how our method can be used for textual editing propagation. Thank you for listening.